Hello, Math 1224. This is Dr. P with Lesson Launch 901, the Polar Express. So take a look at the coordinate plane that I've drawn here. It's the usual XY plane that you see all the time. And I've put a point there. That point is the point 7, 4. And as we get started, I just wanted to think a little bit about what does this mean? What do the coordinates in that ordered pair mean? So what do these mean? These numbers, I mean. Well, anytime I put a point in the coordinate plane, that point can be given two coordinates, which represent, respectively, that point's projection onto the x-axis, which is at 7, x equals 7, and that point's projection onto the y-axis, which is at 4. So really what this is saying, these coordinates are telling us how far out to the right or left in some cases, and how far up or down this point is from the origin. In this case, 7 units to the right and 4 units up. But in this video, I want to talk about a different way of representing a point in the coordinate plane, a different way of giving it coordinates. So I'm going to move down here and draw another coordinate plane and try and draw the same point. So this is still the point 7, 4 in what we call Cartesian coordinates. That's what those coordinates above were called. Those were Cartesian coordinates, and as you may know, the plane that we're talking about is called the Cartesian plane. Now this time I'm going to try and give this point coordinates based on different attributes. So rather than thinking about the projections of the point onto the x and y axes, which are still there, those are still the x and y axes, that hasn't changed. But instead I'm going to base my coordinates on something else. I'm going to base my coordinates on two things. Number one, how far the point is from the origin. So I'm going to give that distance the name r. And then I'm going to give this point a second coordinate based on its direction, based on what direction it is from the origin. And the way I'm going to measure that direction is by measuring the counterclockwise angle from the positive x-axis to the ray that takes me to that point. And I'm going to call that angle measure theta. And the coordinates of this point are going to be r, theta. And these are called the polar coordinates. Polar coordinates. And I'd like to actually just ask the very simple question, although it'll take some work to figure out. It's a very simple question. What would be the polar coordinates of the point that I was talking about just a minute ago? These are the same point, this point and this point. They're the same point, same location. But I want to figure out if a point's Cartesian coordinates are 7, 4, what would be its polar coordinates? So to figure that out, we're going to use a little bit of geometry. So first thing I'm going to do is I'm going to try and figure out what r is. Now to figure out r, I am going to use what I know about the point's x and y coordinates because that gives me useful information about where the point's located. So I know that this point is 7 units out from the origin in the horizontal direction, and it is 4 units up from the x-axis. So I have here a right triangle, right angle there, a right triangle with legs of length 4 and 7. I know that by the Pythagorean theorem, I can say that r squared is going to equal 7 squared plus 4 squared, or in general I would say r squared is equal to x squared plus y squared. And since r is measuring a distance, it's going to be non-negative. We're never going to give r a negative value, at least not for now. We can actually say a bit about what it might mean in polar coordinates for a point to have a negative r coordinate, but I think I'm going to save that for later because it's not essential to what we're doing here. Anyway, so in this case, I get r squared equals 49 plus 16, which is, I believe that's 65. So r is the square root of 65. That measures, by the way, in case you're wondering, that's about, it's not even 8.1. It's a little bit under 8.1, I think. But that measures how far out r is from the origin. So that's going to be the first coordinate in polar coordinates of this particular point. Now finding theta is a little bit trickier because I have to use some right triangle trigonometry. But I know from right triangle trig that in a right triangle, if I'm talking about an angle whose measure is less than 90 degrees, which it is here, I can say that the tangent of theta is equal to the length of the opposite leg. Actually, let me just write that down. opposite over the length of the adjacent leg. I always mean lengths of those legs. I hate when people say the tangent is the opposite over the adjacent. It's the length of the opposite leg over the length of the adjacent leg, but that's an awful lot to write when you're writing on a tablet. Anyway, so that means that tangent theta in this case is 4 over 7. And then I can use my calculator, which you don't see here because it's on my laptop. I'm going to use a calculator to figure out what value theta would have. Now I'm going to do this in radians. Because what we're going to be doing eventually is we're going to do calculus with polar coordinates. So I want to do everything in radians. Calculus, anything in calculus just works a lot more naturally if you use radians. It's not that you can't do calculus in degrees, it's just a bit more of a mess. So anyway, I'm going to figure out what theta is in radians. So I'm going to go over to my calculator and type arctan of 4/7 in radians. Actually, I don't need to type in radians because thank God for Google. By default, Google gives me an answer in radians. Theta is going to be the inverse tangent of 4/7, which is about 0.52 radians. All right, so I can now give this point polar coordinates of 8.1. Actually, I'm just going to give it the exact number that I have there, square root of 65, and then inverse tangent of 4/7. And then if you want something with numerical approximation, sometimes that's more useful to have. You like to know how big something is. 8.1, 0.52. And those would be polar coordinates for this same point, the point that we previously called in Cartesian coordinates 7, 4. So anyway, that's the basic idea of polar coordinates. It's distance and direction. And in the next video, I'm going to talk about how to translate back from polar coordinates into Cartesian coordinates. So stay tuned.